Hello and welcome back to another LeetCode problem. So today we're going to be doing problem number 1502. It's the problem of the day for June 6th, and it's can make arithmetic progression from a sequence. So it's saying the sequence of numbers is called an arithmetic progression if the difference between any two consecutive numbers is the same. Given an array R, return true if the array can be rearranged to form an arithmetic progression. Otherwise, return false. So let's look at these examples. So for 3, 5, 1, it is saying it's true because we can have it like this or 531, but notice that it doesn't matter which way. Like if you can have an array this way where it's you're increasing by a certain amount, you can always have it backwards. So we're just going to check for this case in our solutions. We're not going to check for the other one. And then for 1 2 4, it's already sorted. But as you can see, the gap here is 1, but the gap here is 2, and there's no way to rearrange it so the gaps are the same. Here they're 2 and 2. And so let's think of some ways to do this. So I think the easiest thing you can think of that would work is just sort the array. Right? So you sort the array, you get some numbers, n1, n2, and so on, whatever. Then you just calculate this gap. So whatever this difference is, n2 minus n1, calculate that for the first, and then for the next, for the first combination like this, and then you just keep going down the array and you say, okay, is this difference the same as this first one I calculated, right? So you store this one, call it gap maybe, and then you just say for, well, if you have some more numbers, like let's say you have 1, 2, 4, 5, 6, whatever, you just say like, okay, so here the gap is 1, so I'm going to store that. Let's just call that G. So now I'm just going to check everywhere else, and everywhere else the gap has to be the same, and it's already sorted, so there's no like rearrangement I can make or anything, because it has to be strictly increasing or strictly decreasing. Because if you have something like this, right, 4, 1, 5, let's say, then here be negative and here be positive, so it has to be strictly increasing or decreasing. So that's how you would do it if you sort it. You just get the gap at one place and you check all the way down. Now let's think of something else we could do. So another way we could do this is we could have a set data structure. And what that allows to do is it'll allow us to find all these elements very fast, right? So imagine we store these in a set. So now let's say they're in a set, and let's say we have the same elements, except let's use another example. So let's use an example like this. 39715, okay? So we store all of them. Now what we can do is we know the size of the set, so we know that that's 5. Now what we can actually do is we can get the max and the min of the set, which would both be big O of n operations, right? So we get the max and the min, we subtract them. So we get a difference. So if in this example, it's going to be 8. And then we can actually figure out how big the gap needs to be for this to be valid, right? So how many gaps do we actually have? Well, we have n minus 1 gaps, and that's always going to be the case. And so yeah, so for, if you have 2 elements, you have 1 gap, right? So if you have 3 elements, you have 2 gaps, and so on. So if you have n minus 1 gaps, the whole difference from the start to the end has to be 8. So then it's pretty straightforward to calculate it, right? You just say, okay, give me the difference. So let's say that's 8. And then there's n minus 1 of these. So I just take the length of n minus 1. So that would be like 5 minus 1 here, right? And then you get 8 over 4. So the gap has to be 2. And then you can simply just go from the smallest element and you keep checking if the next element is in the set, right? So you have this set, you start with 1, and then you say, okay, add 2, is that in the set? Add 2, is that in the set? And so on until you reach the most, right? So you try 1, is 1 in the set? Yes. Okay, add 2, is 3 in the set? Yes. Add 2, is 5 in the set? Yes. Add 2, add 7 in the set? Yes. Add 9, and so on. And then you can just make sure that you iterated through the whole set by just having some kind of counter value to tell you, like, this is how many values I went through. And then you stop when your value is the maximum that you calculated. And then you just say, like, how many values did I go through? Did I go through everything in my set? If I did, then the array is able to be sorted like that. So that's the other way to do that. And let's think about the complexities here. So for a sort, right? So sort is n log n time, but there is no space. Now for a set is O of n time, right? We're just going straight forward, but it's also n space. And so let's actually try to come up with a solution that uses both of these, but doesn't use a sort and doesn't use a set. Well, we're going to be sorting kind of like in place, but we don't need a set. And so what we're actually going to do is we are still going to do this min and max thing. So let's just take this same example for the 3, 9, 7, 1, 5. So we are going to take the min and max, right? So let's just say min. And we can simply just call min on this, and that's big O of n times. That's totally fine. Like, we can call something big O of n a few times, and that'll still be big O of n. So we get a min. We get a max. Right? We get a difference, same way, min minus max over and length of the list over 1, or minus 1. So that would just be 9 minus 1, or 5 minus 1, right? So you get 8 over 4 equals 2. And now that we have this difference, what we can actually do is we can traverse the list. So let's say we're at this value here. Can we figure out where it needs to go if we have a difference and we have a min and we have a max? Well, yeah, we can, right? So 3, we know that the starting number has to be 1. So we can say, like, how many gaps is it from 3? Or from 1? Well, if a gap is 2, right, and we're at 3, and 1 should be the first element, then 3 is 1 gap away. And so if it's 1 gap away, it should be at index 1, right? So we know that 3 should be at index 1. And the reason we can do this kind of in-place sort, and it's going to be n time instead of log n, is because we know exactly what element needs to be where. Where in a normal sort, you have no idea, like, what's in your list and what element needs to be where, right? You just have to manually swap until you have no more swaps remaining. But now we actually know what needs to be everywhere. So what we do is we start at an element, and there's a few edge cases here. So the first edge case is we have to figure out, well, how many is it actually away from the, like, how many gaps is it away from, you know, like, actually, no, sorry. So what we need to do is we can figure out where it needs to be, right? So we'll have some value. We can figure out where it needs to be. So that's doable. And that would just be, like I said, we would, the equation for that would literally be, you know, min plus, and then that's going to be whatever index we are at currently, right? So let's say we're at index 0. So where it needs to be is I times the number of gaps. So hopefully that makes sense why that is. Because the first value should be, so let's just look at what the sorted list looks like. So it's going to be 1, 3, 5, 7, 9, right? So the first element should be here. So it should actually be at index 0. And so the place it should be, right, is, or sorry, not the place it should be, the value that should be here. So the value that should be here is the min value plus I times the number of gaps. And so if you have the smallest value, there would be 0 gaps. So then you would have min. And then if you look at, like, what should be here, well, it's the smallest value, 1, plus the current index we're at times the number of gaps. So it's the same thing. So for 3, we should have 1 gap. And so that would be 1, and so on. So hopefully that makes sense why that is the case. So that, now that we know, like, how to calculate it, and by the way, yeah, so when we're at 3, like, this I will be 0. So then the value should be 1. But when we're here, this I will be 1. If we're at index 1, then I will be 1. And so the value that should be there is 1 times the number of gaps, which is 3, right? So anyway, so we use this equation to figure out what needs to be. So let me delete this, actually. Let's just delete all of this for now. Okay. So we use this equation right here to figure out what needs to be at the current index we're at, right? And so at this index, this value needs to be a 1. We calculate that here. So this is I times the number of gaps, because gap is 2 and I is 0, right? So what we can simply do is we can just say, okay, let's just keep changing this number with other numbers until we have the correct number at this index. And then when we have the correct number at this index, we'll just move on to the next one. And what do we actually want to do? So how would be a good way to swap these numbers? Well, we know where 3, so I think I said this before, we can figure out where 3 needs to be, right? So we could figure out 3 needs to be at index 1. And so what we could do is we could actually swap these two numbers. We just go to index 1, we swap them. Now there is an edge case here, And we have to make sure to check it. And so let's say our array is like this. Say it's like 3, 3, 7, 1, 5, right? Or it'd be 9 actually, because we do want to keep the same min and the max. So if we have a 3 and a 3 and we try to swap them, so we do have to check here. If the numbers are the same, then you're going to have a no solution, right? Because then that wouldn't work. So that would be one edge case you have to check for. And if you don't check for that, then you're just going to have an infinite loop. So that's one thing you have to check for. Okay, now let's just go back to our example here. So we swap the numbers. Okay, what does that look like? And then where do we go from there? So we have a 9, we have a 3, we have a 7, and a 1, and a 5. And the nice thing is we're guaranteed to have this be in big O of n, because the maximum swaps we're going to perform is n, because we know exactly what number needs to be in what index. Or like I said, we don't know that in sort. So in a sort, you would be swapping numbers. Like what you'd have to do is you'd have to swap some numbers, and then you'd have to ask yourself, like, did I do any swaps? Yes. Okay, well, maybe you have to do more swaps. I don't know when to stop. But now we know exactly when to stop. Okay, so now we have this situation. Now we ask ourselves, okay, is 9 the number that it needs to be? No, it's not, right? So once again, we have to figure out where should 9 go. Well, 9 should go, it's four gaps greater than 1, right? Because a gap is 2, so it's 4 gaps greater than 1. So it should be at this index. So then we swap these two numbers. Okay, and now what do we have? So we have 5, 3, kind of narrowing its space. Let's make this bigger. 7, 1, 9. Okay, so now we're still at this index, and we ask ourselves, okay, is this the number that we want? No, it's not. We want the 1. Okay, well, where should 5 be? 5 should be over here, right? Because it's 2 gaps away. Sorry, no, that's wrong. 5 should be over here because it's 2 gaps away, right? This should be 1, this should be 3, this should be 5. Okay, so we swap again. Now what do we get? We get 7, 3, 5, 1, 9. Okay. And then, what do we need to do? Okay, well, is 7 what we want? No, it's not. So where does 7 need to go? Well, 7 is 3 gaps away, so 1, 2, 3. So it needs to get swapped over here. So now our solution would be like this. So 1, 3, 5. So this one case happened to just swap everything correctly, but you might have to do some swaps, and then you have to like go farther down and do some more swaps. But anyway, let's say here now we're like, okay, well, is this the number we need? Yes. If we have the number we want, then we just go to the next index. Is that the number we want? Yes. 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 Then we're done. Now, like I said, we can have something where we just have some swaps and then some swaps down the road, and that might be like, let's say you have something like this, right? 7, 5, 9. Then you would swap these two. They would both be fine. So then you'd have this 7, 5, 9. Then you'd say, okay, is one good? Yes. Is 3 good? Yes. Is 7 good? No. Okay, let's swap these two, and then now you'd have the right solution. So you're not necessarily guaranteed to like make all your swaps at the first index, but our algorithm is basically going to be stay at the number that we're at, keep making swaps until it's what it needs to be, and then go down. And by the time we finish traversing, we would be done. And also, the most swaps we can ever make is n. Because once we have a number where it needs to be, right? Like, well, let's say we have some number here. Once we put it where it needs to be, we never have to move it again. Because we put it in the exact right spot, which is why I said, like a sort, if you have a sort where you just have random numbers and you're doing swaps, you're not guaranteed to have that because you have no way of knowing that, right? Like if I just have like 100, 25, 75, whatever, and let's say my algorithm is like swapping two adjacent numbers, well, you have no idea if these two numbers should be here or over here or wherever. And so that's why this algorithm is big O of n, as opposed to like a normal sorting algorithm, which is n log n. Okay, so let's start coding this up and let's go over this. So first we need the smallest and greatest numbers in the array, right? Like we talked about. So min r and max r. And I do think this solution is definitely not an easy solution, the optimal one. An easy solution would just be to sort and then check the differences. Something like that would be pretty straightforward. Or a set would also be easier than this one. So this is definitely the hardest one, but it's also the best complexity. So then our gap is, like I said, it is, you take the biggest minus the smallest and you divide it by the length of r minus 1, right? Because there's n minus 1 gaps for n integers. Okay. And then the other thing we can check here is we know that these are supposed to be integers. So if our gap mod 1, so you could do this, does not equal 0, that means we have a decimal. So if we have a decimal, this is never going to work, right? Like if it's like a 1.7 difference or something, you can't have that with integers. So that's never going to work. So our gap needs to be an integer. Okay. So now we just loop through the array, right? And then we're going to have an integer called should be. And should be is going to be where, like what, sorry, not where. It's going to be what number needs to be at the current index we're at. And that's, like I said, that's from that other equation, right? So it's the smallest plus I times gap. So for example, if it was at 13579, if I is 0, then smallest should be at index 0, right? Because this would be 1 plus 0. And then if we're at index 1, this would be 1 plus 1 times 2, which would be 3, and so on. So should be is the number that should be at the current index that we're at. And then we just have a while loop. So while ri does not equal should be, meaning the number we have is not what we want. Now we're going to have another variable called look at, and look at is going to be in this picture, like let's say we have the 13579. So, I mean, let's just say that we have a 9 here and we have a whatever, 19 here. So we check here what, if it's not should be, then the look at is going to be like, where should this 9 go? And let's look at that index. So that's the look at, is like, where am I putting the number that I have? And then getting another number and putting it back into here. Okay. And so what's that going to be? That's going to be like this. It's a little confusing, but I can talk about it. Okay. And so it's pretty much, you take the difference of like, so whatever number you have, let's go back to our other example. So let's just have, we have this 379, sorry. Yeah, 39715. Okay. So this look at here, if we're at index 0, would be what? So it's ri minus smallest, which would be 2 minus the gap. So it's 2 over 2, which would be 1. So you basically try to figure out like how many gaps forward do I need to go? And then how many gaps forward you need to go from the current number is what your look at is, right? So for example, if we're here and we try to look for 9, so this number should be 3, right? Or sorry, yeah, it should be 3. So, but what you want to do is you want to say, okay, let's go forward. We actually, sorry, we don't look at No, we do. Yeah. So this is fine. So we are just trying to figure out like how many indices ahead we're trying to go. Okay. So that's pretty straightforward. So this is, remember, this look at is where we need to be looking at to swap our current number. Okay. And so we can do this other check again. And this basically just means, like I said, if we try to look at an index, but our equation here, so if this ri minus smallest, like let's say our numbers were like, so yeah, let's say our gap is 2, right? But then we have some numbers like 13479 instead of 13579. So we'd have, and we're at 4. So then we would have 4 minus 1, which would be 3. But our gap is 2. So if you don't get an integer here, then once again, it's not possible. So if the index we try to look at is not an integer, then it's not possible, because we have to have integer gaps at all times. So this is just basically saying like, how many gaps do I need to go? And if that gap number isn't an integer, then we already have a no solution. Okay. And so now the other thing we need to do that I noticed that when I was writing this is you do need to change it to an integer. Even though it is an integer, Python's going to treat it like a decimal still. So we do need to convert that. But it'll still be like, so it'll be like 3.0 or something instead of 3, but you can't access something at index 3.0. Okay, so now if ri, and so this is our last edge case. So this is the edge case where you try to swap two numbers. Like let's say you have some numbers like this, and let's just say you have like 3, you have this case, right? 339715 maybe. And you say like, okay, 3 needs to be here. If you don't check for this, then your while loop will keep running forever, because you'll swap 3 and 3, and then you need it to be a 1. So if you're looking for a 1, but you just keep swapping 3 and 3, it'll never end. And so that's the other case. Is you can't have two numbers that are the same if your gap is non-zero, right? So if your gap is 0, then all your numbers should be the same, but otherwise they should all be different. Like you can't have a duplicate. Okay. So that's the other case, is checking for that. So we can return false straight away here as well. So these are cases where you return false. So if the gap is not an integer, or if the place you need to look at is not an integer, or if the two numbers are the same. Okay, now we swap them, like I showed in the picture. So RR, here R look at, and then this is R look at. Swap them. Okay, and then if you were able to traverse the entire array, that means you have a valid solution, or truth here. And so yeah, so you keep doing the swap until the number at your current index is what you want, and then you keep going forward. And so so you are guaranteed that when you are at some index, everything before that index will be, in the right order. And like I said, you can only have n swaps max, so this should be big O of n. So hopefully this code makes sense to you. And let's actually try to do this with something that fails, just to go through it. So let's put it over here, and instead of having a working solution, let's have a solution that fails. So let's have something like 3, 9, 7, 1, 4. Okay. So our gap here is still going to be 9 and 1, so our gap is still 2, right? So we're going to be at index 0. We're going to say, okay, well, where should 3 be? Well, like we want a 1 here, but we don't have a 1. So let's put a 3, and 3 needs to go here. So we're going to swap these two elements. And so we have this 9, 3, 7, 1, 4. Okay, well, we still don't have a 1 here. So where does the 9 need to go? The 9 needs to go into the very end. So let's do that. So it's going to be 4, 3, 7, 1, 9. And then the problem is here, once you're trying to figure out where this 4 needs to be, well, so remember when we calculate where it needs to be, it's the number minus smallest. So that's going to be 4 minus 1 over the gap. And so here we're gonna run into our edge case, right, where we have 3 halves, which is not an integer. And so now we know like this 4 can't be placed into this. And so if you think about it, if you figure out a gap, the only way for that to be the only solution for something with an equal gap to work is all your numbers have to be evenly distributed, and they can't be the same. And they all have to be a gap away. So you can always do this or some multiple of gap away. So whenever you do number minus smallest, that needs to be some multiple of gap. So hopefully that makes sense why I have these 3 edge cases. And yeah. Okay, so let's do the time and space complexity here. So time, this smallest and biggest are both big O of n. Yeah, this is just big O of 1. So like I said, we are looping through the array, so that's big O of n, and we are doing these swaps, but we're doing n swaps max. So once again, this is just because we have a nested for loop doesn't mean this is actually n squared. It's actually big O of n, because the most swaps we can ever do, since we know exactly where our numbers need to go, is n. So this would be like big O of 2n, right? Like this will go big O of n, and then this is worst case big O of n as well. And like, sorry, it's not big O, this is worst case big O of n throughout the entire for loop, not through one iteration. Okay, so that's going to be big O of n. Space, we actually did it in constant space. And so that's the solution. So yeah, like, remember the solutions we had were sort, which would be n log n, but it would be constant space. A set, which would be O of 1, or sorry, it would be O of n as well, and then O of n space. And then this is the optimal solution where we do everything in place. We didn't make anything else. And that's going to be, we can actually look at like our efficiency here. So yeah, so efficiency wise also, like if you think about it, because one thing uses like more time and more space, I think technically, and because this is LeetCode, if you were to do something like set, your time would be really your time would be really good, but your space would be pretty bad. And then if you were to do a sort, your time would be worse, but your space would be better, and so on. But time and space complexity actually big O wise, instead of just how well you do on LeetCode, this is the best solution you can have. Okay, so that's all for this question. Hopefully you liked it, and I'll see you in the next one. Thanks for watching, and sub and like the video if you liked it. Bye.